Hey, John here. Let's talk about these freestanding applications, okay? And their contrast to what we call a hosted application. So let's start by taking a bird's eye view of what a computer system really looks like, okay? From the bottom up. Solid state physics. You can read all about that from Bell Labs invented a transistor in the 1950s, okay? So they pursued this study of what is called solid-state physics. Silicon is what they really found out was a useful thing, and then we could combine it and do things to it and create these things called transistors. Then a group of people got together and they found out that we can combine transistors together and create gates and latches. These things generally are can be and very commonly are used to execute and perform Boolean operations as specified in the Boolean algebra laws, okay? You can then combine gates and latches to create memories and ALUs and finite state machines that are capable of executing machine language instructions that are expressed in binary. It can be fetched from memory and then inspected, and then this finite state machine that you can build down here would react to it and perform various operations, like, add one to a register and stuff like that, right? This machine language layer, and as we look at this increasingly abstract view of what a machine is, right, as we get to the top here, one could argue it's kind of split in half. Or maybe you could argue that it's split down here between the gates and latches and the machine language. No matter who you talk to, there will be a line in here somewhere where we transition from hardware to software, okay? And usually that's at this machine language layer. It depends on the kind of CPU and the kind of machine language we're talking about. But roughly speaking, you've got these hardware, you've got the gates and latches and finite state machines and ALUs. They come together and provide a mechanism that can be programmed using machine language. You can then create an assembly language. And on many processors, there's a one-to-one relationship between instructions that you can express in an assembly language and what they become at the machine language layer. All right? Now, in RISC-V, we've seen that some of the assembly language that the assembler recognizes, these so-called pseudo instructions, can become more than one assembly language instruction. All right? So this can be argued, certainly in the RISC-V case and in most CPUs, you can say that the assembly language is higher level than just typing in binary values, right? You've got mnemonics, you've got operands. It's easier to read this, all right? So the conversion between assembly and machine language is at the same time not too difficult, and the features provided by the assembly language allows you to abstract away the need to code, these giant, 32-bit or 64-bit binary values all the time, okay? You can then say that languages like C maybe and C++ might actually be between the assembly language layer and an operating system layer, okay? What is an operating system? It's a freestanding program where freestanding is defined as a program written in either assembly language or a language like C and C++ that can be compiled directly into assembly language, okay? Such that the code in a freestanding program needs no help from another program, like an operating system. Hosted applications, on the other hand, require the operating system to provide certain features that these applications can't do on their own. Like, for example, manage memory, open files, close, files, etc. Right? The operating system on most computers manages resources. Quite often they're shared. I'll put quotes around that. Because some operating systems only can execute one program at a time. those days are kind of behind us these days. Most operating systems that most people are day to day familiar with, like on a PC or even your phone, can run more than one of these so-called hosted applications at the same time. And therefore, operating systems, among other things, manage resources that could be shared amongst multiple hosted applications. The concept of hosting an application is referring to the fact that the operating system itself is the host. It creates, for example, an address space for an application. It goes out to the disk maybe, or the SD card or something, reads in a program into some memory that it allocates on behalf of the application, and then it starts that application running along with the other applications that the operating system is tending to over the course of time. So the differentiation between freestanding and hosted, it boils down to freestanding applications run directly on the machine, directly or indirectly written in assembly language or machine language, and they have no services that are provided by something like an operating system. If you want to have a file, you want to talk to data on a disk, you have to write your own code to communicate with the disk drive and partition it up into files if you're writing a freestanding program. That's what the operating system does, okay? In a hosted application, you can do things like, I want to open a file in some directory somewhere, right? Well, the operating system is the thing that says, I know what directories are, I know where they are on the disk, and I'll take care of all that on behalf of a hosted application. When a hosted application says, I want to open a file with some name, all right? That name means something to the operating system that maps it onto the sectors on the hard drive, okay? So freestanding programs have to run on their own with no help from anything. Hosted applications can run, and they can take advantage of all the services that are provided by something like an operating system. All right, so let's look at this Wikipedia page called standalone program, okay? Standalone program is another word for a freestanding program, as is programs that run on bare metal, okay? It notes that on earlier computers like ENIAC and so on that didn't even have an operating system, the only way to write a program was to create a standalone or one of these freestanding programs, and that would be loaded onto the machine and run one after another, okay? And it notes that standalone programs are usually written or compiled directly into assembly language for any specific machine, all right? So just like I said. So this page here might provide some more details and examples if you're interested. If you look at this page here, which is the documentation for GCC, okay, C compiler that we're going to look at in a minute, it talks about the standards that are supported by it here, okay? So if you do a Google search, what am I at? I'm in GNU.org/online docs, GCC standards, and so on. I'll put a link to this in the description of the video below, okay? If you're seeing this on YouTube, I'll put a link to this webpage in here. Now, you sift through here, and there's a lot of technical mumbo-jumbo, but the bottom line is you'll see reference to the ISO standard for the language, the programming language specification here, right? And they have names like ISO IEC 9899, 1999, or the ISO IEC 9899, 2011. These are all different versions and specifications of the C language standards like C11 and C95, and there should be like a C17 somewhere down here, okay? Now, this is not so much, I'm not that concerned about which specific version of the language that we're using here. What I'm pointing this out so that you can Google for these things, all right? What happens is the ISO Standards Committee has open discussions with public forums, and they vote on features that get put into or removed from or changed over the course of time in the programming languages that they specify, like C and C++, okay? And because it's public, the point is all the discussions and the drafts of these specifications are in fact public until they're finalized, at which point you have to pay about $220 to buy them if you want, okay? So that's why I'm making a big stink about this. Google around for this sort of stuff and you'll find the technical specifications if you're interested in languages like C and C++, and you can find the final draft before it was confirmed and you can save yourself $250. Or if you don't care, just go buy the real one, okay? The only difference between the very final draft and the official one is usually a statement saying that, this is the official one that everybody agreed on. Now, I would show you some of these drafts, but I'm not sure that I can on YouTube due to copyright rules and stuff like that. So thus, we are interested in the GNU C compiler site, all right? Now, I've seen the official spec, and this statement here is taken basically directly from it, and it's the one that we want to understand if we're going to write a freestanding program. So let's zoom in a little bit on this here. What we have here in clause 4 of the standard, it says you have two classes of conforming implementations of the C programming language. One is a hosted implementation, okay? That means that it has a bunch of library facilities that are exposing features of an operating system, okay? It also then has a freestanding implementation. That's what we're interested in here. So we can tell the GNU compiler that we want to build a program that is a freestanding program. The compiler will work ever so slightly different, okay? And that, for example, one of the rules for freestanding implementation is that the compiler will only provide float.h, limits.h, standard arg, standard def, ISO 646, standard boolean, standard int, and standard align and standard no return header files. There are no other ones, okay? You can get more if you write them yourselves, but by default, if you create a C program, run it through the compiler, these are the only headers that the system will provide for you, okay? Really quick, the float header file is filled with things like the maximum, minimum value of floating point numbers, how many bits there are in the numbers, and so on. Limits.h is the same thing for integers. Standard arg is the macros and type defs required for variadic functions. If you don't know what those are, Google it. We're not worried about them right now. Standard def is filled with things like the definition of null and so on. ISO 646 is a specification of how do you write a C program if your keyboard doesn't have, for example, a curly brace key, right? Well, that's kind of difficult because you have to use open and close curlies all over the place for function bodies and loops and stuff like that. This header file creates some macros and things that allow you to use words like begin and end for curly braces, all right? And perhaps some other things. It's been a long time since I looked at it. The bottom line is that it lets you write code if you don't have curly braces, among other things on your keyboard. Standard bool is there because in C there is no bool data type like there is in C++. So in standard bool there's a type def that defines the boolean data type, a bool, as something like an integer. Okay, so you can use it like you would in a C++ app. Standard int is filled with definitions like uint64 and int16, uint16, and so on. So you can specify the exact number of bits in integers when you define variables, rather than playing the luck of the draw game by just saying int x, how many bits does that have? I don't know. It depends on all sorts of things. So standard int gives you standard integer sizes if you name your variables correctly, or the data types rather, like the int underscores, int 64 underscore t and so on like that, okay? Standard align allows you to align your variables to byte boundaries like, I have an int or a struct or something, and I want the first byte to be at a multiple of 32 or 64 bytes or something like that. All right, so you can align your data structures in memory to optimize your code if you want to. Standard no return allows you to provide services so that you can tell the compiler that you wrote a function that will never return. Okay, and a freestanding program, quite often, a main might never return. And the reason you might want to take note of that and let the compiler know is because if it does return, it has to save variables, or rather register values, that it may modify when that function runs. Okay? But if it never is going to return anyway, then the compiler can be told not to bother saving those things and save time and memory when it generates code for a function that never returns. Okay? So this is basically all you get to work with in a freestanding program out of the gate. All right. Now, it also talks a little bit about some other issues that come up with freestanding programs, like the fact that main doesn't mean anything special in a freestanding program. In fact, you might not even have a main. How a program starts running is what they'll say is it is implementation defined. Okay, and what we'll see here is that in a freestanding environment, what will happen is we're going to simply write our programs to start executing, and we'll assume that the program counter will be set to 0, and the CPU will simply start executing from there. All right. Now, how a real CPU starts running is dependent on the manufacturer. They may say we'll load the program counter with some other number, like 1000 in hex. It doesn't really matter. There is a spec for every actual machine and every virtual machine out there that'll tell you how the thing starts running. All right. I'm going to use a simulator that starts running by simply loading the program counter with 0 and then letting the instructions be fetched and executed. Okay. So it turns out that whatever's sitting in memory at address 0 is where this thing will start executing when we write our freestanding program. Okay. So let's look then at how we're going to run these. In this video, I'm going to use this thing called RVDDT that I wrote to generate some diagrams for a set of notes that became kind of a book that I was been working on. This thing is available, as you can see here on GitHub. You can download it. Here are the instructions on how to compile it. It should run on any Linux system. If you're on Windows, install something called Windows System for Linux, WSL. Just Google for it and download it from Microsoft. It'll open up a terminal window exactly like the one I'm going to show you here that is running on my Linux system, while Windows can fire up Linux inside of itself and give you the same experience. In such a window, you can execute these build instructions and it will work on Windows. If you need a RISC-V compiler, these are the instructions that I last used and pasted them into my own terminal on my Ubuntu Linux machine on my desktop, and it built the compiler. Okay, now we'll observe that it takes a long time to build this compiler and all of its parts. It is what we call a tool chain, because it's more than just a compiler. It's a compiler, it's the linker, it's the assembler, there's a bunch of utility programs that come with it. All right, it's a big bunch of stuff. If you already have a RISC-V compiler, make sure that it can execute, or rather compile code in this architecture, if you want to run them with RVDDT, which is this application's website I'm looking at right now. If you have another simulator that supports other types of RISC-V environments, like 64-bit or even 128-bit, knock yourself out. But if you want to build a program that'll run on RVDDT, you have to use the RV32i and the ILP32ABI. These are some technical thingies that have to do with how you configure the GNU compiler and its tools, all right, to let it know the kind of executable instructions that it's supposed to generate when you compile your code, okay? And then this website goes on to tell you a little bit about how to run RVDDT if you want to. You'll see enough of that as we move forward in this discussion. Now, if you go back to the top of this web page here, if you download RVDDT, right, you download the code here and open it up and install it and build it, you get this directory here. And you have a source directory. This is the RVDDT source code of the simulator itself that you can build. And then we have these example programs in here, okay? We're going to talk about these freestanding programs right here, okay? There's some other ones here as well, but these are the ones I'm going to go over right now. These are standalone 0 through standalone 10. Maybe I should have called it freestanding. I left the free off, okay? So in the freestanding subdirectory, in the examples are these 10 example programs, from the simplest to the fanciest one here, right? So let's go through them one at a time and see what's going on. This README JRW file, by the way, gives you a bird's eye view of what each one of these standalone programs is supposed to do. So I'll leave this open and we can come back to it from time to time as we go through each one of them. First thing we're going to look at is stand 0 and stand 1. Stand 0 is going to be the crude long form instructions of an assembly language program that would start itself running and do just enough to run a program in what we would recognize as an address space that has a text, a data, and a BSS, and a heap, and a stack. Okay? Stand 1 is going to use the pseudo instructions to do the exact same thing, but as I say, in an understandable manner. This code is going to be easier to read, okay? And then each one of these from there on forward will increase the functionality of what it's doing and keep getting closer and closer to the point where we get to stand 10 down here, when we can run a regular C program that actually has a standard library, and you can use functions like, malloc and free and string copy and things like that from the standard library. All right. Let's do a quick review of what our address space needs to look like in order to run a useful C program on our machine, because it is going to be our responsibility in our freestanding program to create the address space and initialize it so that the C program can function. All right? The C program, when it runs, expects there to be a stack, and it expects the stack pointer to be pointing up here at what we call the top of the stack. So as things get pushed, the stack pointer will work its way down from its address down towards 0 as the stack grows in size. It'll then move it back up when it shrinks. The heap also needs to be initialized, and as we know, it'll grow upwards as more and more memory is required by the program to create objects using new and delete if it's C++, or malloc and free if it is written in C. Okay? The BSS needs to be zeroed out. The data and the text need to be copied in from or initialized by the output of the compiler so that the instructions and the initialized data variables are all sitting in memory at the proper addresses before the program starts running. Okay? So what do we need to do? We need to get the stack pointer set to what I'm going to do is I'm going to set it to the first address, the address of the first byte that's not in the actual memory of the machine. So if our machine, for example, has exactly 2000 in hex bytes, the bytes will be addressed, their addresses will be 0 through 1FFF. Okay? Therefore, the stack pointer for a full descending stack will have to be initialized to 2000 in hex, all right? So that when we push, we subtract from it, make a space to hold something, and we put it in there, all right? So the stack pointer will actually be set to, just because the memory happens to start at address 0, we're going to initialize the stack pointer to the actual number of bytes in the memory, which turns out is one and the same as the first address that actually is not in the memory of the machine. Okay, so somebody has to initialize this stack pointer. Somebody also has to zero out this BSS. These are the sort of things an operating system would provide for you. Okay, but we're going to have to do it ourselves because we're freestanding. Okay, now we know that on a RISC-V, somebody also has to set the GP register to point to the beginning of the data plus hex 800. Or more accurately, it has to be set to wherever the compiler expects it to be. Okay? And we'll see how that works in a little bit later, okay? Now, the simulator that we're going to use is going to take care of setting our stack pointer to this address for us, okay? Now, I'm sort of cheating in that regard. It turns out that our code that we're going to write that's going to initialize everything could easily set the stack pointer to any value it wants. We can even write a program that goes through memory, modifying and reading back values until all of a sudden the memory doesn't work anymore, where you get an error, or you could write in 1, 2, 3, 4, 5, and you read it back and you get FFFFF and stuff like that. And you can scan through memory to test it, to probe for where it might end if you wanted to. And that all depends on the kind of machine, whether or not it's a fatal error to do things like that, or simply something where you just start to recognize that the memory stops working all of a sudden, okay? Now, the simulator that we're going to be using is going to set the stack pointer to the number of bytes in the memory, which will be this number up here, because every time we run the simulator, we can actually just choose a different size. All right. And rather than rebuilding our program and changing the instructions to change where the stack pointer is initialized to in order to move it around and change the size of the memory of our simulated machine, it's just easier to let the simulator pass in that number by simply setting the stack pointer before it starts running our otherwise freestanding program. Okay. So let me change colors here. We can note that this is going to be specified by the simulator. It's going to take care of that for us. Even so, we're free to set it and move it to wherever we want in our own freestanding code. All right. I'm going to write it, though, and present it in this discussion such that the stack pointer will simply be initialized for us. Okay, just to make it easier. If you write real embedded systems code, you're going to be setting this in your program based on the amount of actual physical memory in your machine, because it's not going to be as mutable and dynamic as it can be with a simulated environment. So what else is a simulator going to do for us? The simulator is going to read in a binary file into the text and data regions in here. So the simulator will load in our executable binary data, our instructions for the text, and the initialization data into the data region in here. And that's sort of faking it a little bit, but if you actually got a real system that was with embedded ROMs and flash memory and stuff like that, it turns out what you do is you would program this into a flash memory inside your embedded chip. And it would miraculously have been placed into the machine from the perspective of your freestanding program. All right? So our simulator allows us to just poke this in here. The simulator will set the program counter to 0. The simulator will set the stack pointer up here beyond the end of memory so that it is suitable for use of a fully descending stack. All right? This is not that different from what would happen if you just went out and bought a so-called system on a chip, a SoC, okay? Very much so, when you power it up after you've programmed it, it will come to life with the program counter set to some known address. Your compiled code will be in the memory of the machine somewhere, presumably, where the program counter was aiming, okay? And it'll be up to you to write the instructions to finish the initialization of where the other registers and stuff like that, partition your memory up how you need it for your particular application, and start everything going, all right? So if you grab the files from the RVDDT GitHub web page and you copy it to your local machine, this is what you get. You get the examples and the source code, all right? So if you go into the source code directory, oops, if I can type, it would help, and compile it, all right? Then you go over to your examples. One of the examples are freestanding programs, and you see stand 0 through stand 10, and the README file that tells you what each one of them are for. Let's look at the first one, all right? Now this file name, CRT0.S, is a very common name for the startup code for a freestanding program. What it stands for is C runtime 0, as in the first thing. The big S means it's an assembly language file that needs to be run through the C preprocessor before it is assembled. If it had a little s in here, by default, it would not be run through the preprocessor. I tend to write all of my assembly language programs with a capital S, so that I can put things like pound include and things like that in here, all right? And pound define and stuff like that. That's not going to be happening in this particular code, but out of habit, I just do them all that way. So that's what's going on there. Let's take a quick look at what's going on here. In this compiler, and this can differ if you get a compiler from somewhere else, a different vendor or something. What happens is I can put .text here, and it says anything that follows here, all the data that I'm going to define and instructions and stuff, put it in the text region of the address space, okay? This here says if you see a symbol called _start, make it global. Like as if in a C program, what you would do is, if you declare some function int XYZ, that is global by default, right? If you put static int XYZ and you wrote a function, it would be a local function. All right, so this here is akin to creating a function in a C program like this. I'll put a little comment over here. This is like saying, maybe it's void _start like that, and you might have some code in here. All right, and that is in stark contrast to what would happen if you said this, right? If I said static blah blah blah, this is not a global function. All right, so putting something like that over here means that this label will be global, all right? This here is there. You'll see it in a lot of programs. I only included it to let you know, to recognize it if you download code off the internet or poke around a little bit. This will be very common. This is a message for the debugger and the analysis tools that come with the compiler to let it know that start is the name of a function as opposed to something else, all right? While we're at it, there's a thing down here that says size of the thing that's represented by the symbol start is equal to .-start. This thing is used to create a piece of data in the load module that comes out of the compiler, or in this case the assembler, to let debugging tools know how many bytes there are in the start function. All right, that's just, again, these help the debugging and the analysis tools. You could leave them out completely and your program would still work. You don't even need to make start a global function if you want. You don't even need to put a label here if you don't want, okay? Why? You'll see in a minute, because we're writing a freestanding program, and as long as we put instructions in the text region, and the text region starts at 0, they will simply execute one after another as you see them right here, okay? Now, this is version 0, and it's there in all of its ugly glory, only for illustrative purposes, all right? So let's take a look at this and then move on to the version written with the pseudo instructions. Without a pseudo instruction, you have to load the GP register to initialize it, and we'll see there's a symbol that's provided by the link editor to tell it where it's supposed to point. This is the name of the symbol that represents the address that you're supposed to put into the GP register. And these, as you can see, are the ABI names rather than the X names of the registers, right? The GP register is X3. If you can't remember that, go grab yourself a copy of the RISC-V spec or RVAL-P. I'll put a link to RVAL-P in the description of the video. And in here, we give you the ABI names, like the application recommended use, right, of each of these registers, and they give you the name, a standard name for that. So the global pointer GP is an alias, another name for X3. The stack pointer SP is another name for X2 here, and so on. So what do? We're going to grab a program counter relative delta distance value to this symbol from the currently executing instruction, which by definition is, this one has to be at 0 as the first instruction in our program, okay? And we're going to put that into the GP register. We're going to add that to the program counter and stick that in there. That's what OWPC does. Then we're going to add the remaining bits, right? The low order 3 hex digits in order to calculate a 32-bit value that's stored in the GP register, all right? Now notice this push, no relax, all this mumbo jumbo in here. Relaxation has something to do with optimization that the link editor will do if we don't tell it not to. Now, the reason we have to shut off right now for these two instructions is because what relaxation is it lets the linker know that it can optimize access to the memory and the data in the BSS if the addresses that it wants to refer to are close to, plus or minus 2K, the value in the GP register, which is this symbol here, okay? Now, the reason we have to shut it off, we have to be sure to have it off in order to do these two instructions, is because the linker will optimize this code away. And what it will do is it'll set the GP register equal to the GP register, and it won't make any sense. So in order for it not to optimize this code and to explicitly load the address of this symbol into the GP register, you will see this at the beginning of all freestanding RISC-V programs, okay? What happens after that, right? So we have to zero out the BSS. Here's a loop that zeroes out the BSS. How do you do that? Well, we're going to load a register with the symbol that represents where the BSS starts. We're going to load another register with the address of a symbol that represents where the BSS ends, all right? Now notice this comment up here. We're going to zero out the BSS segment starting at BSS start, and we're going to poke a bunch of zeros in there all the way up to and include BSS end -1. There probably should be a close parenthesis right there, okay? This is because, as we'll see, the BSS end symbol is the address of the first byte past the end of the BSS region. So we will code the loop down here accordingly, right? If you wrote it in C, maybe this would be the equivalent condition here, right? Branch if greater than or equal to unsigned is the instruction we're using here. What are we going to do? Is A0 greater than or equal to A1? If so, we know we're done. We go down here, and when we're done zeroing out the BSS, we're going to just halt, all right? That's all we're going to do. We're going to initialize our address space and then halt the processor here. That's all this program's going to do. Now, what's an A0? What's an A1, right? Well, A0 is BSS start, so that's an address that's less than or equal to the address in BSS end, right? It turns out these two will be the same address if and only if there's no variables in the BSS region. All right, in which case we'll get down here. This will be true the very first time it's executed, and we'll just come down to the e-break. If this is false, because there's variables in the BSS, what will happen is we'll store bytes one at a time whose values are zeros. Register X0, as you know, is always set to 0, and we're going to store that into 0 off of A0, because A0 is going to be the pointer that we're going to scan from start to end here. We'll see in a second. We're going to store zeros in there one byte at a time, as if, A0 is a pointer to a character, for example, in a C program. We're going to set it to 0. Then we're going to add 1 to A0. We're going to bump it up to the next address, okay? Then we're going to do an unconditional branch. And they don't have one. So how do we do that? Well, we ask, is the value of X0 equal to the value of X0? Well, of course it is, right? 0 is always equal to 0. Therefore, the condition will be true in this branch, and it'll go back up to clear BSS, which is right here. And then ask, am I done yet? All right, so it'll just add 1 and store bytes into memory one at a time until the whole thing's zeroed out, and then fall out the bottom down here and stop, okay? Now, this code's a little bit messy. Let's not even run it. Let's go over to stand 1, because this is the exact same code written using the pseudo instructions, and you'll see it's a little bit more readable, all right? We again have all the same startup up here, the start, the global, all that stuff, right? We have our no relax thing in here to let it know to do this instruction and not optimize it away. Simply load the address of this symbol into the GP register. Do what is necessary to make it so. That's what this pseudo op does, and we'll see it'll expand into the same two instructions we just saw in the last example. We do the same thing to initialize A0 and A1, and this loop is the same that we just saw before, and when it's done, it'll go down here to the e-break. So let's go ahead and compile this and then run it. First, we compile it. What do we do? Well, when you compile a freestanding program, you tell the compiler, I want it to work in freestanding mode. You can set some other options as well in here. I'm going to say do not generate position independent code. That's another advanced feature that's normally used for shared libraries. It may not be required for this particular example, but I'm going to leave it in there anyway. You can read about that in the compiler specs if you want. We're also going to tell it, I want you to generate instructions that can run on an RV32I machine. And if you're going to call subroutines, use the standard ILP32 specification for the application binary interface, all right, which is essentially use these registers for these purposes in this table here, okay? So that's when it compiles and assembles, in this case, the CRT0.S, and it converts it to a .o file, an object module. We then fire up the compiler again, and we give it a few more arguments down here this time. We say no standard library, put the text of the executable image at address 0. Don't relax anything, which makes the no relax note inside of here redundant, okay? But we'll see, we'll run it without that and we'll see some differences, okay, just for fun a little bit later. We're also going to say put the data region in memory starting at address hex 1000, okay? Create an executable file called prog out of this object module here. Now, this executable program is what we call an ELF format, right? ELF, which stands for Executable Linkable Format. Now, our simulator does not know how to load an ELF file, all right? So once we're done compiling and creating this executable image in ELF format, we're going to use a utility called object copy. We're going to copy this ELF file to another file called prog.bin. And what we're going to do is we're going to convert it into a raw binary file. In other words, we're going to extract the data and the text regions out of this ELF file and put them into a single file that is the raw image of what's supposed to be in memory when the program starts running. Okay? This makes our simulator easier to write because all it needs to do is load in a binary file and then set the program counter to 0 and let her go. All right? Now we're also going to use a utility called object dump, and we're going to use it to create a listing file. Okay? So this will give you a clue at what's inside an ELF file. What is this doing? obj dump. This tells it to use the X names for the registers when it disassembles the program to dump it out. It's going to read this prog file, which is the ELF file, and it's going to create a prog.list file. Let's just cat that and have a look-see. What is in here? It knows that we're little endian RISC-V mode, and it lets you know that it's a 32-bit executable in ELF form, okay? And then it's going to disassemble the text region. Now, it knows about the labels and where they are. These are the addresses in memory where these assembly language labels were placed, okay, when the thing was linked and made executable. All right, you can see the labels over here as well that we saw in our code. This is a pretty nifty disassembler, okay? Now, because we're disassembling from the ELF file, it has all this extra debugging information, like the symbols and where they are. It's not just the executable raw binary data. Otherwise, all we would see is this and the OEPC and this over here. We wouldn't see these comments over on the right because the disassembler would not know what the intent was of these instructions, all right? So that's the kind of debugging data that's stored in the ELF file along with simply the executable hex values, the binary bytes and stuff like that, all right? So let's look at this in relation to the CRT0.S file that we looked at before. These two instructions right here comprise that LA pseudo instruction that says LAG3, or the GP register rather, which is X3, according to the ABI. It generated these two instructions that we saw in stand 0 example, right, when we coded it by hand. But we use the pseudo instruction. It'll take care of that ugliness and just make it so that it works, okay? By generating the two instructions and specifying the symbol for the global pointer and calculating the correct value for OEPC, which it decided to set it to 2. Okay, remember, this is 0 extended to the right, 3 hex digits. Then it's added to the current program counter, which in this case is 0. And the sum of those two is stored in x3. So this will effectively set x3 equal to 2 with 3 zeros after it. Now we'll see in a minute, the global pointer is not at 2000. It's really at 1800. Okay, so what it's going to do here is it's going to subtract the decimal value 2048 from x3, which equals 2000, and it's going to get hex 1800, which I'll show you in a minute is where the global pointer symbol is supposed to be. So these two instructions here are what LA GP, comma, global pointer dollar accomplishes. These two here is the LA of the A0 register, which is also known as X10, right? If I want to set X10 equal to the beginning of the BSS, you'll notice this label's wrong, right? We'll see about why that is in a second. This thing here is going to ultimately set X10 equal to this value right here, which we'll see is where the BSS begins. It also just so happens that these two instructions down here set the same value to another register. This is A1, also known as X11, to the same value over here, right? The fact that these two have the same value, we'll see in a minute, is why the disassembler is confused as to what symbol belongs over here. And we'll see why that is true in a minute. Down here is our loop that we hard-coded in all of its glorious detail, so you can recognize this one flat out. Notice that there's little comments over here that the object dump program lets you know. If I say BEQ to this thing over here, it notes, by the way, this if the condition is true, in this case it always is, it will go to this symbol here at clear BSS, which is over here. This one over here does the same thing. It says, oh, by the way, when this condition that the branch instruction evaluates is true, it will branch to done BSS, which is down here. And that's what our program is supposed to do. All right? Now, if we want to run our program, I wanted to save some typing, so I added a rule to my make file here. In these examples, I can say make run, okay? Which depends on prog bin. So if it's not there, it'll compile it. And then it'll run the RVDDT simulator. This here is how you tell it how much memory to simulate. And this here tells it what program to load into the memory starting at simulated address 0. Okay? And this is an interactive debugger. So if I say make run, what it'll do is it'll load up the binary file into the memory. You'll notice it prints out, FYI, I'm initializing your stack pointer for you, doing you a favor. And I'm going to set it to this number here because that's what you told me up here to make the size of the memory. Okay? It also notes I've read in prog.bin and I put it in memory at address 0. Now you can type in commands like D, which dumps out the memory. Okay? Every time you type D, it'll just do the next set. Right? If I say D0, it'll go back and start dumping from 0 again. All right? So this allows you to repeatedly advance forward. Okay? There's another set of instructions. You can always type question mark, and it'll give you a little list. Oh, here's all the things you can do with RVDDT. What we're going to do is trace instructions, okay? You can say starting at some address and go this many, okay? Or I can just simply say TI and say start wherever you are right now and execute this many instructions, right? If I type R, okay, it'll dump out all the registers in the CPU. So here are all the registers right now. The program counter is currently set to 0 because our machine just booted. Stack pointer right here is set to 2000 because that's how much memory we asked it to create and simulate. All right, all the other registers are initialized to FO, 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 FO because they are not yet been used for anything. X0, as you can see, is always 0, no matter what, all the time, every time. All right? So if I say TI, it'll execute one instruction and it'll print out what it is. Afterwards, if I want to, I can type R. I can also type T, which will trace one instruction, and before doing so, it'll print out all the registers. We call this a pre-register or a pre-trace register dump, okay? before we trace this instruction, here's the values of all the registers, okay? Now, if you dump out the registers before you trace this instruction, it tells you everything that was the state of the machine before the instruction was executed. And this over here will give you a comment that says this is what this instruction will accomplish, all right? So, and that's just how this particular simulator works. Everyone is different, okay? Radically different. So what I did here so far is I executed 2 instructions. This one up here and this one down here. And the effect of doing these 2 instructions is that I loaded the GP register with this value here, 1800, okay? So before I did anything at all, this was the state of the registers. Notice X3 is this. After this one, I changed the value of X3 to 2000 in hex, and you can see that it changed there. Here's the second instruction here. If I dump out the registers now, after that has run, we see we changed it to 1800, okay? Now, we don't need to register dump out this the whole way. We'll trust that they all work fine. In fact, we don't need to do them all one at a time at all. Let's just say continue running the next 100 instructions, or until you run into an illegal instruction or an e-break, all right? So this is a nice way to see what's going on, all right? So what this thing did is it loaded the GP register up here. We looked at it in great detail. Then we load up the A0, right, which is X10, with the value of 1000 hex. We load up this A1, which is X11, with the same address again, okay? And then we asked, are we done zeroing out the BSS? Because the beginning is equal to the end. There is no BSS. Therefore, it's going to go to address 28. Otherwise, it would fall through to address 1C, okay? Because we're done, we hit the E-break down here, all right? So that's what you do with RVTDT to see these programs run, all right? So that's how you can simulate these things. Let's go on to standalone number 3 and do something for real here. Now what we're going to do is we're going to fire up a C program, all right? So we're finally doing something real. Okay. We see all the same stuff, except for rather than finish clearing everything out and then stop right away, we're going to say call main. And as a note, I put in here, just like the GP register details in stand 0, I said, you know, the call main is going to accomplish this, all right? The pseudo instruction call will expand to 2 instructions down here, okay? So this is going to initialize the BSS and start main. And main will run when main, if and when main returns, okay? It'll come back here and it'll execute e-break and stop the simulator. So let's see what's inside main.c. What does it do? It does absolutely nothing, followed by return the value 8675309 in hex. All right? So if we make this program, we see something else for the first time. We compile CRT0.S into a CRT0.O. We compile main.c into main.o. Now the link editor has something to actually do. It links these 2 object modules together into a program called prog. And all these other flags we already talked about, they're the same values we've been seeing all along. We then make a binary file out of it, which is the thing that we load into the simulator. We also take the OBJDump utility and create a listing and disassemble what came out of the compiler. So we see what we recognize up here. We also see the 2 instructions that came as a result of the call pseudo instruction. And again, you see the little comment on the jailer down here. It says, yeah, 12 off of X1 after this OWI PC up here, supposed to equal 34 in hex as the target address over here, which is, by the way, the same number as this symbol main is over here that came from the main.c file, all right? So here's what the compiler did to compile a C program with a function called main that simply says return some hex value. Well, it does a LUI to get the 8675 in there, and then it does an add immediate. Now keep your mind about you with all these different number bases, right? You got hex here, decimal 777 turns out to be the 309, okay? And it puts that into X10 because the ABI says that register X10 and 11 for larger values are not only argument 0 and 1 that could be passed to a subroutine, they're also the return value from subroutines that have values to return. So it makes perfect sense that main decided to put this value here into x10 and then jailer to 0 off of x1, right? Because the subroutine calling conventions for RV32 is use a jailer with a target address of the function you want to call and put the return address of where the function is supposed to go back to in x1. And that's what this one instruction here does. So it makes sense that when main is done, it's going to jailer, throw away what would be the return address if main was using this to call a subroutine, okay? And then go to 0 off of x1, all right? So what jailer really is doing here, they don't have a return from subroutine instruction. It is effectively doing that by just going to the address that's in the x1 register, plus 0, and saying throw away the side effect that jailer would normally accomplish, which is store the address. In this case, it would be 40 of the instruction that would be executed after the jailer down here, all right? So there you go. We can now run this program. We can see what it's going to do is the exact same thing before, and then followed by jump over to main, do this, and then jump back to return, all right? So what do we know? We know the program's sitting in memory starting at 0. We can see there's a few more bytes than there was last time. If I just say TI 1000, that should be more than enough to do the 10 or so instructions in here. We see the usual startup to set those things. We see it trying to get ready to zero out the BSS, but there is nothing in the BSS in this example. We then see the OEPC jailer pair, which accomplishes the calling of main. We see what main does right here in these two instructions, and then we see a jailer back to where it came, which is address 30 down here, okay? Because jailer x1 to 12 off of x1 here would have stored a 30 into x1 because that's the number of the instruction that comes after this jailer, okay? Which is this e-break down here. If we dump out the registers, it should make perfect sense that x10 right here, if this is x8 and that's the value there, there's x9, here's x10, there's the hex value of the return value from main, okay? So far, so good. Let's look at stand 4. What's going on in this one? Well, no changes to the CRT0.S. But what's happening in main? Well, we have some integer variables that are globals up here, and they're not initialized. These variables are going to be in the BSS. We have a 4-byte integer here, and then we have 16 bytes in an array of 4 integers here. We're going to store that 8675309 into the last element of the array B2, and now we're going to return a 0 from main, okay? Let's run this one, okay? Again, we're still running it the same way, simulating 2000 in hex bytes, load in the program.bin file, okay? And we can run it. And this time it took a little bit longer. Now, why did it take longer? Because you can see right here, it's zeroing out the BSS. Okay, remember, this sets the GP register to the 1800. These two instructions here were setting the address of the beginning of the BSS into register X10, which is this 1000. This pair of instructions down here sets the first byte past the end of the BSS into X11. And that's why we now go into the loop and says if x10 is greater than or equal to x11, we know we're done. And we're not done because it has to zero out 14 in hex bytes, right? 16 plus 4 for those two variables, all right? So you'll see it go around and around and around and around and around in the loop. That's what all these are. And it finally gets done down here somewhere when it asks... if, 13 is greater than or equal to 14? No. It does one more time around the loop, and then it asks if 14 is greater than or equal to 14, and now it's finally true. It branches down to 28, which it calls main right here. Main, what does main do? It puts 1000 into x14, because that's where the BSS starts. That's one of the variables, right? And you can see it putting this 8675309 value into X15 down here. And then what is it doing? It's going to store the contents of X15 into 12 off of X14. Now, up here it set X14 equal to the address that's the beginning of the BSS. 12 bytes off the beginning of the BSS is probably where the fourth element of that array of integers is, okay? Then what does it do? It adds 0 to the contents of register X0, which is 0, puts it into X10, which is the variable that holds the return value, and it returns from main, and it does an e-breakdown here, okay? So we can see what's going on. Let's take a look at the LST file in this case, right? Here's the main. We just saw that all taking place, all right? Now that we've got a little bit going on here, let's take a closer look at something else that's in the ELF file using the NM program. Well, let's first just run it and look and see what it does. What this is going to do is it's going to list up all the symbols in the ELF file and tell you, by the way, BSS end here is at that address. Data begin is at this address. Something called sDataBegin, which is not our concern, also starts at that address. BSS start is also at 1000. Now remember when the BSS was empty and the list program gave you the wrong names for these here? In fact, it gave you the wrong names again. In this case, it says data begin and BSS end. What we want to zero out is from BSS begin. Now, why is it printing the wrong thing here? Because in our CRT0.S, we clearly said BSS start to BSS end. And I'll apologize for the uppercase, lowercase inconsistencies. These are simply the standard names that have evolved over the years for these labels that are attached by the linker. You can change them if you want, but they become unstandard at that point. Okay? Now, the reason this is wrong is because data begin is 1000 in hex. So is BSS start. The disassembler doesn't know which of these symbols to use because all it knows is that it's dealing with an instruction that put that value in a register. So the FYI to us is it simply grabs the first symbol it finds with that address. So we have to apply a little, cranial capacity to understanding what's going on here. All right, all these three things are the same value. It'd be nice if it told us the one that we put in our code, but that information's gone. All it knows is here's a label that's near this that might be helpful to you. Okay? In this case, it could be confusing. If it confuses you, don't look at the labels. Look this up and then go find out where it points yourself by looking at the data down here. Now, normally when I do NM, I pipe it into sort. Because if you look at this, you got 14 before 1000, before 1800, before 1000, another 1014 before 0. They're out of order. It's very annoying, at least to me. So if you sort it, this will sort it alphanumerically. It'll put all these addresses in ascending order, okay? And for those addresses that are all the same, it'll use the data that follows. It's still not in the best and most beautifully readable form. However, the numeric values at least are sorted over here, okay? So clearly the start comes before our clear and finish BSS, and then we have the main, and we can see that BSS start is at 1000. We can see that B2, that variable, starts at 1000 in hex, right? And it turns out that we know that B2 is actually part of the BSS region, right? It's not part of the data region. You'll notice the data begin and end of data all have the same address. That means there's 0 bytes in there. All these symbols are meaningless to our program right now because we're not using that section, right? So what we're really looking at is BSS start, one variable here called B2 that starts at that address, another variable called B1 that starts at 1010, okay? That means that B2 is 16 bytes long because the value of this address for that variable is 16 in decimal, less than whatever comes next, okay? And this one here is just an int, so it's only 4 bytes, okay? And that's why BSS end is 4 bytes past the beginning of B1, right? And down here represents the end of all the text data BSS. And here can be used to represent the beginning address of your heap, okay? And now you see this global pointer down here. When the linker builds all this stuff and puts all these labels in there, it goes back and looks at where the beginning of the data is, okay, at 1000 in hex, adds 800 and says, this is where I think you should put the global pointer. All right. Now, this is a little more complicated than that because the compiler does play a bit of a role in there, but this is beyond our discussion right now. What we care about is something somewhere tells us where we're supposed to set the GP register, and they give us a symbol so that we can put it in our CRT0 file. Wherever that is what needs to be in the GP register, because the compiler may decide to use that register, and when it does it, it will assume that it will have the address of this symbol in it, all right? So we need to make sure that we do that right in order for all this stuff to come out. All right, so let's move on to standalone number 5. All right, so I forgot which one this is. Let's look it up on the old website here. Now we're going to call main and set the values of variables in the data and the BSS regions. All right, so this one is just going to be the same thing, but we're going to have more variables. Some of them will probably have initializers in the main here. So, well, let's look at our CRT0.s first. We can see no changes in here. Clear out the BSS, call main, and then abort. No problem. What does main.c do? Ooh, okay, so now we got a couple variables that are initialized, and they're real big too, okay? We have 1,000 integers in here. That means there's 4,000 bytes in use here. 4,000 bytes in use here as well. And we still have our B1 and B2 with no initial value, which will be in the BSS. So these are going to be in the BSS. These are going to be in the data region. They'll be initialized with these values by the compiler, all right? Before the program even runs, those values are going to be in the memory, all right? That's what this up here is going to do. When we run main, we're going to set, what, B2, the last element of B2 to this, same as the last program. Then we're going to alter the D3 and the D2 arrays. These are so-called named because B stands for BSS, D stands for data, all right? So what we're going to do is change the value of the first element of D2 here to this number here, and then we're going to change the value of, D2, or D3, D2, all right, to these two values there and return a 0, okay? Make this up. All right, let's look at the LST file real quick. All right, the usual CRT0 jazz up here. We can see that main's going to do some fooling around. You can see the 8675309 here. You can see it being stored at a negative, 176 off of X14, because up here it's at X14 to 3000 in hex, right? Well, the compiler can do this however it wants, okay? So as interesting as it might be to poke around and look in here, the bottom line is this is what the compiler generated, okay? And when it's done, it jailers back to where it came from, which will be up here, and it'll stop, okay? So let's go ahead and run this program. Wait a minute. Before we do this, let's do this. Because we need to keep an eye on where the data begins, right? Now, we knew that because when we compiled it, we said it right here, okay? But it's nice to confirm that we didn't do something wrong, okay? So all the executable text is here. Now we've got the data region here. You'll notice the global pointer has a really funky value. Like I said, it doesn't necessarily have to be the data region plus 800 in hex. The compiler decided to tell the linker, don't put it down there. And the reason it did that, by the way, is because I made D3 so big that if it stuck the global pointer way down here at 1800, it could only be used to access D3, and it would not be of any value to access any of the other symbols down here, if the compiler so decided to do so, all right? So, again, this funky thing, just simply set that GP register to whatever the symbol says to do so in your CRT0.s file. Now we see the BSS starting, we're down here. We see the ending of the data. All three of these symbols have the same address, okay? A little confusing. So what we have is the beginning of the data. We have these variables in here. We then have the end of data, okay? Followed by the beginning of the BSS, and then the first variable here in the BSS, the second variable in the BSS, and the end of the BSS, okay? All right, so if we run this, what should happen is the interesting stuff is down here at hex 1000 and hex 1FA0 and 2F40, okay? Now, it's a little annoying that they're spread out that much if we want to poke around and look in the dump, but I wanted to make them large to show you that the global pointer does not have to always be down here plus 800, okay? Because if you put big data items in your data region or in your BSS, then the global pointer would move too far away to be of any value, all right? So again, we can dump out the memory. We can see executable instructions here. Notice all these zeros in here. Did we zero out? And we didn't even run the program yet, right? And yet there's all these zeros. This isn't because we zeroed out the BSS. Why are they there? Because I told the linker to put the text at address 0 and the data region starting at address 1000. And because we converted the executable file, the ELF file, into a binary file, and had absolutely no option whatsoever than to just pad the memory so that the data region would start at address hex 1000. So the OBJ dump added all the zero padding so that this would start in the right place, okay? These zeros are not because we zeroed out the BSS. This is zero padding at the end of the text region, all right? The data region starts here. Notice again a bunch of zeros. Why are there zeros here? It's because we initialized this array. Remember we set it to like 1, 2, 3, 4, 5, or it looks like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 in decimal, right? And these are little endian values, so the value 1 is 00000001 in hex, right? So these are the first, 10 elements, 10 in decimal elements of the like B2 array in the data region or whatever. And because we initialized it, we have to initialize all of them. And if you don't initialize an integer in an array, all the uninitialized ones will be set to 0, even in the data region, okay? We go through this for a while, and we'll see the other array that was initialized, oops, we just went by it, to some other values, right? Remember, one of them was like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and the other one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so here's the other array that was initialized in the other order, okay? And all of the other values in that array, okay? Now let me exit out of here because I can't remember where the BSS started, right? So the BSS starts at 2F44. We just looked at the contents of D3, D2, and how they were initialized. We can see the D1 up here at 2F40 if we want to. All right, it'll just load the same way. So let's dump out this value here. And now we're seeing the first byte. Remember all those D's? D, 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 D. That is the value of this D1 integer here. All right, so the data region ends here. So why are these all uninitialized? And what are all these FFFs in here? All right, well, we didn't execute any code yet, so CRT0 didn't zero out the BSS yet. So there should be more zeros down here. We are responsible for that in our CRT0. These FFFs down here, look at the address, 3000 in hex. How much memory was allocated for this run? 3000 in hex. These are non-existent memory addresses, okay? The simulator simply prints them out as FF. Okay, so what happens now? If we just trace a whole bunch of instructions and let her go until it finishes, it's nice to see that it ended by jallering back from main and into the e-break that we remember from before in CRT 0.0 as at address 30. Okay, so let's now look at the memory here. All right, we initialized the BSS, we called main. Remember, main set the first value of each of its two arrays to some other thing. The 7, 8, 9, 6, 5, 4, 3, 2, 1, 0, and so on. And if we just dump out all the memory and scroll forward until we get, through the 1,000, right? And here's the beginning of the second array in here somewhere. Here it is. And that one was set the other way around. This is the 1, 2, 3, 4, 5, 6, 7, 8, okay? That was poked in there in the main. And then we can dump out memory until we see the end of that, which was what, like 2F40 or something like that. So here we go. There's the variable that was set to DDDD. We didn't change it in the main. Here's all the zeros that we used, that were initialized in the BSS, as well as one of the variables that was modified. One of the values, remember the fourth element of that array was set to this 8675309 variable. Okay. On initialized data here. And what would be the stack way down there? Now, how come the stack is all A5? No one stored anything in the stack. Well, remember how the ABI for RISC-V works. If you call one subroutine and it returns, and the subroutine only uses registers that don't need to be restored, it doesn't need the stack at all. This is what we call a leaf function. It has no other subroutines. If main never goes to call anything else, it doesn't need to remember and save X1, right? Because remember X1, it would have to save that if it calls another subroutine. Otherwise, it wouldn't know where to go when it's done, okay? So what else? If it needs to use more than a handful of the temporary registers, it might need to save some of the saved registers, right? This thing only needs 2 registers to do the job. So there's actually nothing to put in the stack. It's completely optimized away. So that's one of the nice things about an ABI that allows you to use the registers for arguments and return values in functions. In some inner loops, you can call subroutines that are very optimized so that they never have to reach out and interact with a stack and reading and writing memory. It can all happen just using registers, which goes much faster than if it has to interact with the memory, right? And update caches and all this other stuff that's going on. If you ever touch memory, if it's just sitting there using regs inside the CPU, this thing works fairly well, all right? Now, granted, this particular program does write values into memory here. All right, you got me there, but there are functions that you could write that don't necessarily need to update variables in memory. Calculating factorials and things like that would be entirely just dealing with registers. Now, let's look at standalone number 6. What's it going to do in here? You're going to create a character array in the main that I never use. All right. So the funny thing that's going to happen here is the entire array and all the initialization for that array will be completely optimized out by the compiler. All right. This is just a little side note so that you know not to get confused when you see things like this happening, which is really quite an eye opener as to how smart the compiler can be at times. Now, this one you could argue is pretty obvious. If you create a variable that's supposed to go on the stack with a bunch of bytes in it, set it and you initialize it to something and you never read it, you never write it or anything, who cares? The compiler is going to throw this whole thing away and just return 0 in here. As you can see in the main, all it does is set 0 into the return value in X1 or X10 rather, and goes back to the CRT0. We don't even run this. We know what it's going to do, right? Okay, just a little side note. Optimization can be very interesting. Now let's go back and look at standalone number 7. Standalone 7, you'll notice this is an error, okay? Well, I'm going to do this one on purpose because this is where we're going to go from really trivial little programs to actually using C programs. So what's going to happen is I'm going to create an array just like I did in standalone number 6, but this time I'm going to use it, okay? So what's going to happen in here? Well, let's open it with the editor here. This time I'm going to create a 100 element array. I'm going to set it to 1, 2, 3. I've also got some stuff sitting in the BSS up here. I'm going to call this thing called myfunc, and I'm going to pass it the address of this array. Now my func is written in a different file. What is this going to do? Set a variable to 0, and then it's going to add up the values of all the bytes in this string until it reaches the null terminator. And then it's going to return the sum of all those bytes. Okay? So what does that mean, right? What was the array had in it, right? It's an array of characters, but they're going to be set to these decimal values. Characters are really just integers anyway. These are not characters that can be printed, is my point. This is 1, 2, and 3. The values of those bytes in this array are 1, 2, and 3. If we sum those up, we're going to get 6. Right? So if I compile and run this program, it's going to have a BSS region. It will not have a data region. You're going to see main create this on the stack and pass an address to it, to my func down here. My func will run and do some stuff and return the sum. This is starting to be a program that will actually do something real, right? Uh-oh, what's wrong with this? The compile failed. See this? Undefined reference to memset. If you go off and read the detailed doc of how the GNU compiler works, you'll see that it says that if the compiler needs to clear the memory to do its job in the code that it generates, it's not going to emit a loop that will do it. It'll simply call the memset function, and it'll expect you to provide that somehow. Well, one way to get it would be to say, well, all right, I know I'm making a freestanding program, but I can link in code from the standard C library in order to achieve linking my program, all right? So I can provide that code from my standard library function somewhere, all right? So in order to do that, we have standalone number 8. And what we're going to do is we're going to add these arguments to the compile line, all right? So let's go into stand 8 over here. Let's just do a make world in here and watch how the compiler runs. We'll see the flags down here. The usual thing to compile the CRT0, the main.c, myfunc.c. Look what happens when we link edit this thing. All the same stuff. Don't help me. Put the text at 0. Don't relax. Put the data at 1,000. Create an executable program called prog. And make it out of CRT0, main.o, and myfunc.o. And see these two guys down here? What those are doing is it says to the link editor that when you're combining all these files, if they are subroutine calls and any of these object modules that are not defined anywhere, go look in the C library and the compiler standard library. Otherwise, we made no changes to the stand 7 versus stand 8 here, okay? And we have the LST file and all the usual output. So let's look at the LST file before we run it. Now, you'll notice there's a whole lot more code in here, and what we have are the executable instructions for memset, which came from a library. What's up here? What's that thing? That also came from a library. And now we see things we recognize up here, like myfunc. That's the thing that we wrote. There should be a loop in here, right? This might be the condition that ends the loop, and then like an unconditional branch or something, or maybe it's a bottom-driven loop that goes back up to the top, all right? So if you unravel this, you can see the loop in there, followed by, what's it doing here? It's actually setting extended with 0 and going back to here. I guess it optimized the code so that it can deal with the case where there's nothing in this string differently than if there is something that's summed up in the string, all right? I'll leave that as a task for the viewer to go through and figure out why the compiler chose to generate that particular code. And here's the instructions for the main. Here's the CRT0 code up here, okay? So what's going on with this stuff? We're at memset, and what the heck is this thing? All right. Well, this libc init array is there because I called it. Okay. If you read the documentation for the standard C library in the tool chain that we built with the instructions from the RVDDT GitHub page, Buried in the documentation, it will say if you use any standard library functions before you call anything, call this. And its name suggests this is going to initialize something in the standard library. If you don't do this, who knows what's going to happen, all right? I didn't write the library myself, but I do know, because I read the doc, that I need to call this before I do anything like call memset and stuff like that, all right? It turns out that memset probably does not need to be initialized. If you unravel that code, I'm sure it would work without me initializing the library. However, other functions do need to be initialized. So you definitely just want to do this every time, okay? If you're linking against the library code. Now, if we run this, you'll notice that we also allocated more memory this time. You're going to see it executes a huge number of instructions. Oops, TI 1000000. All right, if you go through here, I'm not going to walk through all this. I mean, if you want to knock yourself out. Just a quick glance. Remember, this is the usual stuff at the beginning of CRT0. It's going to zero out the BSS, and we see this iterating over here. It's looping, and when that's done, we'll see a pattern change like down here. And then what we're going to see is it will call the libc init function, which is probably going to be a jailer like right here, okay? This is probably the code that's in that libc init stuff. I don't know what it's doing, but it's doing a lot of stuff. And eventually, if you look at the addresses over here, it'll go back down to some low number. That looks like a return from subroutine call kind of a thing. And maybe 64 is back in CRT0. I don't know. It seems a little bit high. But it would then call main, and maybe that's what this is doing here. Main would do its job, and it would call, you know, the myfunc, and there would be some looping going on in there, and it would add up the values and return it and so on. And if we look at all the registers when we're totally done, register 8 is here, register 9 is there, register 10 is there. The value in register 10 is 6. That's the return value from main, which is what it should be. It called myfunc, gave it S. S adds up all the non-zero elements until it reaches a 0 and returns that sum. Main then returns it. The sum of 1 plus 2 plus 3 is, in fact, 6. And that's what we got. All right? So far, so good. Compiler works. Simulator works. Everybody's happy. Let's look at standalone example number 9. Okay? What's the README file say about that? Oh, it's another one that's supposed to fail. What are we going to do here? We're going to call malloc, and it's going to fail because there's no sberk function. Aha! All right, so let's see what happens. We're in stand 9. Let's compile it, and we see we have a problem. In fact, we have 2 problems. Notice that the text is set to start at 0. The data is set to start at 1000 in hex. We're putting more and more and more code in our program, but the linker is still being told to start the data region at 1000 in hex. Now, eventually, the text region is going to get too big for that to happen, and it just did, all right? That's what this overlap stuff is all about, okay? So this is telling me I made the data region too small. It's also telling me, you know, barring that problem, I still can't build an executable program anyway because somebody wants to call a function called sberk and there isn't one. And that brings us to standalone program number 10. Now this one is the whole gamut. You'll notice I added a thing called stub standardlib.c. All right, let's go back to the comments here. Note that the text region is too big to hard code at 1000. So we'll notice that I changed that value to make more room. And then the other comment here is that I added stubs to make the standard library stuff satisfied in the in this thing called new lib. All right. New lib is the name of the standard C library that comes with the GNU toolchain for RISC-V. All right, if you Google around, this is a very popular library that's used for freestanding programs. All right, we don't want to have to write every single one of the functions in standard library, so we can go simply get them and have all kinds of functionality at our disposal. However, in order to use newlib, which requires us to call that, library init array thing that we just looked at a few minutes ago, we also have to provide some other functions so that it can do its job. Like, for example, if I want to allocate memory, I have to move the break line up and down. And the newlib library doesn't know how to do that, because that's the job of what would be, if there was one present, the operating system. So let's look at what's inside here. All right, if you read the documentation for newlib, it will say, in order to use these functions, you have to call that init array thing, which is in the crt0.s, which we saw up here. It says call this before you make use of the standard library. Then it also says provide a set of functions whose behavior is, as documented. All right, so I provided this little file. And I did exactly what the doc said, all right? Now think about this for a minute. We're trying to use the standard C library. And that library was designed to be used by hosted programs. But we don't have an operating system to host that program. So what we have to do is fake it, okay? So of all the things the library does, it has it whittled down to only a few dependencies. Like, for example, what happens if you call exit in your program? What's it supposed to do? Well, the newlib has no idea what to do. It depends on what you want to do with your freestanding environment, okay? So what I'm going to do is I'm going to provide an implementation of exit that simply just calls eBreak. Just stop, okay, the simulator. What if it calls kill? All right, now if you can read the doc on how all these work, these are all in section 1 of the man page on Unix. Man 1, kill. All right, what does it do? It's, or not section 1, section, 2. All right, these are the operating system API calls to the Unix operating system, all right? If I call kill and I give it, a process ID number and a signal number, it tells you what it would do. Oh, it'll go to that process and it'll send it a signal and blah, 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 blah. And it'll say, if you call kill and it worked, it'll send a 0 back. Otherwise, it'll send a -1, and it'll set this thing called error no to one of these thingies down here if it fails for some reason, all right? Now, we don't have an operating system, and we don't have multiple processes. So we can't send a signal to another process. What we're getting at is don't use the kill call, all right? However, if you're going to use the library, you have to satisfy the fact that it needs a kill subroutine in order to use that library, okay? So what we've done here is we've provided an implementation. Now, it's debatable what to really do in here. If somebody, think about this for a minute. First of all, you're writing a freestanding program. You wouldn't sit there and think to call kill to send a signal to another process in your freestanding, environment where you only have one thread of execution. So this is on you. Don't do that, okay? If you do, this is just going to call eBreak as written here. Arguably, you might just simply ignore that in return and let the program keep going. Okay, I chose to do this because it just makes no sense for anyone to use the kill function at all. All right, what else we got going on here? You read the documentation for getPID. This is a way that a process can ask what the operating system ID number is for the running process. Now, again, we don't have any OS and we don't have multiple processes, but it's certainly not a death warrant to our application. We can just lie and say, oh, you're process number 1. You're the one and only one there. Anytime you ever ask, you're process 1 and you're still process number 1, okay? So these are just stubbed in to make sense, all right? So what do you do if the program decides to close a file? Well, first of all, we don't have a file system. We don't have an operating system. We have no disks. We have nothing. So you should have never opened one in the first place, and we'll see in a minute. We also return an error if you try to open one. But if you do call close, I'm going to just simply say the file descriptor you gave me is bad, and I'm going to return an error here. Okay? Because no matter what, if you called close, that must be, by definition, a bad file descriptor number. What if you ask about the status of a file? Okay? Now, this gets a little bit more advanced, but what we're doing here is if anybody ever calls fstat, we'll simply come back and say, the file that you are asking about is a character device file. In other words, it's something that is connected to a terminal on a screen that you can write to, and it would be displayed somewhere. In this particular case, it won't be displayed anywhere. We'll just throw it away, as we'll see in a minute. But you can still implement a stubbed out version of fstat that returns something quasi-meaningful. All right? Now, you're not going to call this yourself in your freestanding program. However, you might use some routines in the C library that might call this on your behalf that you may not be aware of, okay? That's why we don't just simply say eBreak in here, all right? We can return a value that makes sense, that doesn't cause a system to fail, just to placate the library. We can ask, is this given file a TTY? Is that a terminal? Sure, yeah. Any file that you think is open, we'll let you think it belongs to a terminal screen somewhere. lseek. This is really only useful if you actually have a real file on a disk. It lets you move around in the file and read it in random order. All we're going to do is return 0, which is the value that suggests that whatever you wanted to do has succeeded. Right? We're going to ignore any request at all and just say, yeah, sounds good. Thank you. We took care of that. Okay? What if you try to open a file? No. Okay? Error. This error means that we've exceeded the total number of files that can be opened on the operating system. There are no more file descriptors available for your process. And in a way, that's true. You're allowed to open exactly 0 files. So if you open another one, we've run out, okay? What if they ever try to read from a file? Well, no matter what they do, we're going to simply return, you reach the end of file. Again, that makes sense, right? Now, they should never call read, but if anything does, it'll just keep hitting the end of file no matter what happens. What if they try to write to a file that was never opened or anything? Well, just simply throw it away and return, yeah, thank you, I wrote whatever you asked me to write, this many bytes. Again, just placate the library. We finally get to something useful down here. This is the thing that was missing, all right? Look at the dock up here. The operating system has to manage on a real operating system, right? With all the virtual memory and all that other stuff. So if you have a library like newlib, it can't just simply say, here's more memory that I'll allocate to some variables because that program asked for it. It really has to defer to somewhere else in order to change the position of the break line, which is the end, which marks where the end of the heap is. Okay? And normally, when you have a hosted environment, this will go into the operating system. The operating system will look around. It'll try and figure out how many more virtual memory pages need to be added to your page table. How many PTEs need to be created? Where do the pages come from? And all that stuff, okay? The newlib can't do that for you, okay? This has to be provided by your runtime environment, your hosted environment, or we can implement one of them on our own. Now, the semantics of this sbrt call is we get this delta value, and it says when delta is positive, what it means is that the newlib code wants to move up the current break line to allocate space for more variables. If delta is negative, it's asking to move it back down. You know, you've deleted a bunch of objects, or you called free in a C program to free up a bunch of memory, and the library has decided it no longer needs that memory, and it moves the delta back down again. So in order to do this, we simply have to keep track. Remember earlier on I said there was this _end symbol, okay? in a C program, if I declare an extern char array and I give it one of those symbols that I happen to know that the link editor is going to provide me, this allows a C program to know about the address of what could be thought of as an array of characters. Okay? So then I declare a static pointer to a character and I initialize it to that symbol. Okay? So what I now have is a variable that's initialized to the address where the heap begins, which is the end of the text data in BSS. That's what this symbol means. It comes from the linker. Okay? So this thing is persistent because it's static inside this function, right? And it's initialized, so this will go in the data region. We'll see this end of data variable, okay, if we do an NM on our program. So what is this thing going to do? Well, what it does is it says, remember the semantics of sburk is that it returns the address that the burk was set to before this was called. So we need to save that before we modify it. So the only thing we're really doing in here is satisfying the fact that when sburk returns, we can always return the old value as a pointer to a character according to the official specifications. We just simply need to keep track of the current end of data while the program runs. So if he allocates memory, delta will be positive, 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 positive. This end of data thing just keeps moving up. We just need to keep track of where it is at all times. That's all. That's the total job of this thing. Now, you could do other things in here, too, if you really wanted to. You could ask things like, well, look, has the end of data become really big and dangerously huge and running into the stack, for example? You might want to stop the program if the guy, allocates too much memory, because otherwise the machine would crash in a very unintuitive manner, most likely. But what we're doing here is the absolute minimum. We're going to assume that any program that decides to allocate memory is not going to allocate too much. It'll behave itself and not cause a problem. Now, granted, that may be a very foolish assumption, but to do anything more at this point in time would be an enormous amount of work, and I'm out of time. All right, so let's go ahead and compile this one up. Let's take a look at, let's clear this back out again. Let's first look and see what this program does, right? So what does main do? Main, this time, instead of just declaring an array that's on the stack, I'm going to allocate memory out of the heap for it. Then I'm going to copy the hello world string into it. Then I'm going to call the myfunc, which is the same code we saw before. I didn't make any changes in there. And remember what the sum of all these bytes are, okay, whatever the ASCII codes are for each of these letters in the space here, will be what's returned from myfunc, right? Then we're going to free up the memory, and we're going to return the sum like we did before. So what's going to happen is malloc here is going to call sburk to move it up by 100 in hex bytes, which is 256 in decimal, okay? When it's done and it says free up memory down here, it's probably going to free that memory back up and move the heap back down, all right? Now, I say probably because it depends how the new library code implements its heap logic. It might not actually move the break line back down. It may hang on to it and reuse it later on, okay? So this may or may not lower it back down, is my point. So let's compile it up. Let's do nm on prog and then sort that. Have a look at what's going on now. All right, now we brought in a lot of stuff. You recognize these in the CRT0. You recognize the main and the myfunc. You recognize all these because they came from this stubbed in standard library routines, okay? There's the init array function. There's the malloc and the free functions. And look at all this funky stuff down here. All the way down to here look like subroutines because the T here means it's in the text region, right? D means it's in the data region, and so on. You can look up all these letters in the manual for the NM command because that's what's printing this out, okay? So what do we got in here? We got a bunch of stuff in the BSS region, I suppose, down here. Well, there's the data begin, all right? And it's got a bunch of junk in here. There's the global pointer, end of data. There's my variable that I called end of data, all right? With this funky number over here, right? That's what the compiler decided to call the symbol for that static variable in there, okay? And it's a lowercase letter over here, so it's not a global symbol. It's there for my reference. I can see that it's located in memory there when the program runs, but this symbol here is not global, therefore no one, the linker won't use it. If somebody else has something with the same name, it won't collide, all right? That's what that's all about. So the end of the data regions here, the BSS then starts, and there's a bunch of stuff. Some of the items I put in the BSS here, the error no comes from the library, along with, you can recognize all this malloc stuff, total memory and top pad, however it is implemented, it needs these variables. It also has some symbols way down here, again, from the library that it might need for whatever purposes, okay? Now we can go ahead and run this, and we'll allocate plenty of memory for it, right? The 3,000, okay? And when we compiled it, also notice that we increased the beginning of the data, right? It didn't start at 1,000. We moved it up to 1,400 because this code in here goes too far, right? The data begin is at 1,400 because I said so. If you look at what's going on in here, the free function might start down here at DE4, but it's gigantic. And it goes past the 1,000 in hex mark, all right? That's why it was griping about overlapping regions before, okay? So we did a make run on here. If we want to, we can say trace instruct. We can go and look at every single one of the instructions one at a time if we want to, or we can just run it until it stops on its own, okay? Dump out the registers. We'll see that X10 is set to this hex value 41C. Well, I don't know. I'll leave it as a task to the viewer to go through and add up the ASCII values, right? If you type man ASCII on a Unix system, it tells you, right? A capital H in hex is 48. In decimal, that's a 72, right? So it would add together all these values. If we can do it in hex, or rather in decimal, right? It'd be 72, and then what was it said? Hello world in there, so there would be an E in there, so it'd be plus 101, plus 105, 108, that's L, and then another 108 for the second L, and so on. In decimal, there's your O, and a space is a hex 20. It's like over here someplace, right? The space is this. In decimal, it would be 32, and hex it would be 20. If you add all that stuff up in hex, hopefully, if my program was written correctly, it would come out to 41C in hex to add those letters together, all right? So what do we know? We know that we have everything we need to download and build a compiler that generates RISC-V executable programs and link them together in some utilities to see what's inside them and so on. And we have this new lib that, when combined with these stubbed-in functions, allows us to write C programs that run in a freestanding environment. All we need to do is initialize our address space in CRT0, provide a couple of stubbed-in routines to satisfy the needs of the new lib, and then we can write C programs that use all the standard functions like malloc, string copy, and free. Now, you can take this a lot further if you want. You can stub in the entire C++ library too if you want. New lib provides that as well. That'll be a subject of a whole different discussion, but the short of it is you can look it up and it'll tell you we need to provide these operating system level functions. And C++ will have something very similar to this sberk down here. That has to do with how do you handle newing and deleting things, all right? It's a little bit different than this, all right? But it's the same kind of philosophy. And you can find all that documented as well, all right? So you could easily write another one of these set of stubs is my point. All right, so this video is getting a little bit long, but let's do one last thing before we call it quits here. Let's look once more at how this is compiled, right? We got the text at 0, the data at 1400. and we still have no relax set as a global option. And as I mentioned before, technically, the only time we really need to have no relax turned off, or on rather, is when we're setting the GP register. Okay? Let's look at the LST file real quick of this thing. How many instructions are in this whole thing? The last one's at 1108 down here. And that's with us saying we do not want the linker to optimize out instructions to simplify the code. All right? And it does that by using the GP register from time to time, as well as if it figures out that there are these pairs, like in CRT0.S, where it's doing the Louis followed by an add immediate kind of a thing, and it decides that it doesn't need to use both of those instructions. It could only use one, for example. All right? It can optimize it away. So what we can do in this particular make file is we can turn off the no relax flag right there. Okay? We're disabling the disable, which effectively enables it. Okay? So we're allowing it to relax when it compiles. All right? So let's compile it again. And cat out the LST file again. Notice we're using less bytes now. Okay? So obviously no relax did something. It removed instructions. It did certain optimizations. Let's see if we can find one. Well, obviously, right here at the very beginning of our CRT0.S, it's already optimizing. Okay? These two instructions set the global pointer. But this instruction right here, look at what it's doing. It's using X3, which is the global pointer, in order to calculate the address that it needs to put in X10, which is the beginning of the BSS that needs to be zeroed out. It's using X3 again down here to calculate the address for the end of the BSS over here. Okay? So that's what relaxation is. Okay? And just for fun, let's turn off the relaxation up here in CRT0, and you'll see what it does up there. It will not do something that makes any sense to anybody here. You'd think they would have put a special case in the compiler for this if you're setting the GP register itself. But, whatever. Let's just comment this out. All right? This push pop stuff has to do with save whatever the current options are when you're assembling, because I could have set some other ones above. Then turn off relaxation, and then restore the options, which includes things like no relax, to what they were before we got to this line of code. All right, that's really what's happening here. But because I now don't turn it off anymore, let's see what happens to this first set of operations here when this code is built. Okay. Let's see what happens now. Look what the first instruction is now. Add immediate 0 to X3 and store the results in X3. Now, right after the hardware is reset, do you really think that this one instruction here is going to have the effect of putting this number here, which is supposed to be the value of the global pointer, into the X register, or the X3? I don't think so. All right? So this is the whole reason we have to play this special game. You can either globally say nothing's relaxed anywhere in the entire program, and if you do that, obviously, you're slowing down your execution of your code by adding a lot more instructions, okay? Or do we just want to do the one and only one case right here when it really matters, okay? And yes, that's obviously a rhetorical question, okay? So here we go. We're back to normal again. Put 2,000 into X3 and then subtract, 1024 from that value, resulting in putting 1C00 into the X3 register so that it can be used down here for various optimizations and things like that. So let's go ahead and put our make file back the way it was. Oh, that's the CRT0. Ugh. point is to remember what these addresses are, because I forgot last time. This is 1004 with no relax removed from the make file. We're only setting no relax for the very first instructions in CRT0 up here, okay? That's the state of this current compile here. Now, if I edit the make file and we take this and say, never let anything be relaxed anywhere, recompile everything, and then, again, cat the LST file, we almost have 100 in hex bytes. That's 256 bytes in decimal plus 4. That's actually 260 bytes of wasted memory of all these instructions that relaxation allowed the linker to remove. Okay? So that's not bad. Okay? In fact, 100 in hex out of about 1,000 in hex is 1/16th, right? That's about an 8% reduction in wasted memory. Okay, so this is useful. And also keep in mind that our little test program here is tiny, right? This program does nothing. Think of what happens if you wrote a real program that did anything truly useful. Just how many instructions would be removed and how much faster this thing would actually run. So you definitely want to have relaxation as much as you can get it, but not when you don't want it, when you're dealing with the CRC0.S. So thanks for watching. I'll see you next time.